background. But so I'm going to give a very quick outline. The linguist should be patient with my being very rough on this background. But just to summarize, especially for the mathematicians, there is this approach to linguistics, and goes under the name of generative linguistics. It started out in the mid-50s and been mostly developed by Chomsky and school. And the key idea behind that is that, in some sense, there's the large-scale structure of language, by which I mean syntax, is some kind of computational process, and you can try to understand what kind of computational process it is. So this is kind of an introduction for mathematicians, so I stress this point of view. And an early phase in generative linguistics was sort of centered around the idea of using formal languages as a way of modeling the way that grammars and syntax works. I'm saying this because, although this is kind of going way back in the past, most mathematicians that have heard something about generative linguistics, they tend to be familiar with this formal languages point of view. And one point that I want to stress is that it's important to kind of get beyond that point of view. And so the early phase was centered around studying the properties of formal languages, the different type of grammars that you can characterize. This famous Chomsky hierarchy result in terms of what type of automata can recognize such languages. But of course, when you apply this formal languages point of view at actually describing natural human languages, you see that the actual production rules that you have to describe in order to describe parts of syntax of actual languages become quite involved. Comment for the mathematicians in some sense is like, if you every time you had to do anything with groups, you would only be able to describe them in terms of generators and relations. That's pretty much what these formal languages do. There's a more appropriate sense in which this is true. Representations of group gives rise to formal languages. So it's a proper comparison for the mathematicians. So in some sense, one can see already from this fact that it's desirable to have simpler and more natural kind of generative models for syntax. And also there is another point that's quite important to stress, and I'll say a few words more about that, which is the fact of interpreting, trying to describe syntax and language in terms of strings versus structures. And this is where this minimalism approach to generative linguistics becomes particularly relevant. So let's go a little bit more into this comparison between these approaches. So the one idea is that syntax is characterized by the fact that you can have certain kind of recursive structures. We can nest sentences inside other sentences and so on. And in particular, from the point of view of formal languages, you can characterize what type of recursions are possible according to what type of grammars in the formal languages sense you can use. And for example, one of the very early, this goes back a very long time, but one of the first ideas of whether this class of context-free grammars and formal languages would be enough to describe human languages or not. And one of the first examples of a counterexample to this claim is actually Dutch, which is a language where you can have this kind of cross-serial dependencies which are not realizable by a context-free grammar. I think Rini was the first one who came up with this counterexample. And so in general, oops. So in general, the one thing is that in terms of formal languages, what you see is exactly this type of thing. So you see certain strings, certain sequences of letters in the alphabet in the formal language. You can think of the words in sentences, and you describe properties of these sequences, like this type of recursions that you can get or not. But in some sense, you can think of language as sequences, or you can think of language as some kind of more interesting or more additional structure to sequences, which is this point of view in terms of generating trees. So more precisely, when you think of it in terms of formal languages or in terms of the automata that compute the language, you're really viewing the language as a kind of a time-oriented sequence of events, which are the transitions in a certain automaton that computes the language. And the question is whether this is really what the languages look like or not. And if you want, the idea is like this. This formal language point of view is telling you that this is what languages look like. But in fact, this is what languages look like. And so the idea is how, whether it's a better way of describing the generative process of syntax in languages that looks more like this and less like that. And so that's one way of trying to introduce what this minimalist point of view actually does. So the minimalist model for syntax was introduced by Chomsky in the early 90s, and it underwent several versions and several developments over the years. And one thing that we actually do discuss, especially in the second paper that I mentioned, is some kind of comparison between earlier formulations of minimalism and the most recent ones in terms of their underlying mathematical structure. But let me jump directly to the most recent formulation. This is based on a series of papers that Chomsky had been writing since, I think, around 2013 or so. I believe that's when he started to develop this new version of minimalism. And the one key idea behind this is that the generative process of syntax depends ultimately on one simple operation, which is what he calls merge. And this is actually the main focus of what I'm going to talk about. What are the properties of this basic operation that governs the generative process of syntax? And one can think of the actual construction of sentences as a two-step process. There is this core computational structure, which is this one that's based on the single operation of merge. And then there is a second step process, which Noam calls externalization, which is where you actually start to differentiate things between different languages. That actual different languages have different syntactic parameters, different kind of word order structures, and so on. But this is sort of, the idea behind this model is that there are like two separate steps. And there's like a core computational step that's language independent in the sense that it's not affected by the specific syntactic parameters of a particular language. And then there's an externalization process where all these additional structures start to play a role. Okay. So what are some of the goals of or at least some of the ones that I will be discussing in this talk of the work that we've been doing? So one is to actually show that this core computational structure of merge has an extremely simple and transparent mathematical description, which is uses things that are well known in the mathematical setting, and what Noam describes in his papers as the action of merge on workspaces, which I'll say more about in a moment.
Roberta. The speaker microphone is muted.
She couldn't hear me before, so I don't know if they can actually hear us.
Which, Anna, which?
Which room? D21, 104, I think. And there's another room that I booked. I don't know if they moved there. I also sent her a message. Oh.
Why? How? I didn't touch the thing.
Hello?
Can you hear me now?
Yeah.
Yeah. Sorry,
Okay.
I read the chat, so you don't need to start chatting with each other, okay? I read the chat and try to solve it, okay?
Roberto, yeah? Which room are you in at the moment?
109. It's
109.
yeah. Okay, we start again. Let's share. Again. No, not from the start. Where is the talk now? I lost it. It's here. Where was it? Oh, no. Up, here.
Okay.
Perdón.
Fixed. Okay. Hope everything is working. Right. So I was saying, okay, there is. I'm going to talk a little bit more about it later, but there is this kind of useful, comparison between this structure in linguistics and the kind of analogous structure in physics. Also, one can observe that several kind of desirable linguistic properties of merge that often are listed in the linguistic literature on the subject as sort of axioms or requirements that they don't actually have to be imposed in addition to the subject because they actually follow directly from the mathematical structure. So they are actually part of the package already to begin with. And also, there other observations, like Rini had some explicit observations about why, if why this binary operation that this merge operation that we'll describe better in a moment, is expected to be a binary operation, so with two inputs and one output, rather than an n-ary operation with some larger number of inputs. And one can observe from empirically analyzing linguistic examples that would, if you postulate an n-ary operation with n3 or larger, you would have phenomena of both under-generation and over-generation with respect to the binary merge. And this also follows directly very easily from the mathematical structure. You can actually count precisely the amount of under-generation and over-generation that you would get. So a lot of these properties become very transparent if you just formulate it in this language. So let me just get down to be a bit more precise about what this whole structure is. So what is this core computational structure of merge? So in this very basic form, it's something that mathematicians usually call the free non-associative commutative magma, which sounds that's its name. So what is it? You can think of it in two ways. You can say that, so first of all, it's a set with some operation on it. Right? So as a set, you can say that it's a set with elements are balanced bracketed expressions in a single variable x. So something like this. Balance means that every time you open a parenthesis, you also have to close it. And then it's just another symbol besides the parenthesis. Okay. And the operation is the one that takes two such expressions and puts them together by adding another set of parentheses. Okay. And there is an equivalent description, which is to say that the elements are actually binary rooted trees. And so I've been drawing them like this, but you should not imagine these as being in the plane. I'm not fixing a planar embedding for these trees. So for example, if I flip it around like this, or that, it's the same tree. So the choice of a planar embedding is irrelevant. It's a very important point, actually, from the linguistics perspective, and I'll come back to that in a second. So one can think of it in these two ways, and either you think of the expressions like this, or you think of the trees, and these two points of view are completely equivalent. And the operation in this, if you think of them as trees, takes the two rooted trees and attaches the two roots to a new root above them. So now let's think about, so you can describe a kind of generative process that gives rise to these elements, that generates this entire magma. And so let me introduce, this is kind of a formal trick that mathematicians use all the time. We are interested in describing a certain set, but we put on it a tiny bit of extra structure. So we form a vector space on the elements of that set. So this just means that formally you can write sums of these elements. This is simply a way of, if you're looking at the list of possibilities to actually put them all together into one object, which is the formal sum of them. So it's just a convenient, bookkeeping device of the objects that you are analyzing. So there's nothing very deep about that. And so here's, I have a kind of note for the mathematicians about what this vector space becomes in terms of this operation. Magma is again something that's a known object in mathematics, but the point here is that you can also decompose this set into pieces, or compounding this vector space into pieces, where you keep track of the length, right? It's like the leaves of these trees would be, if you look at the leaves of these trees, it would be the sentence, right, that you are building. So you can kind of decompose these things in terms of the length of the sentences. So this is kind of like a grading that you have, as you look at increasing lengths that you can form. And if you put together a kind of formal variable that has one variable for each possible length, you can write a kind of a fixed point equation. So x is now your unknown of your equation, and you set, so this is a fixed point because it takes x as input, and you say that the output has to be again x itself. So it's what is there such an x that when you put it together with itself, it stays the same. Okay, so that's an equation. Is there such an x? But so because you have all these degrees by increasing length, it means that you can try to solve this equation in a recursive way by increasing lengths. Okay, so if you do that, you just write it out in terms of these graded pieces, and you see that the end piece depends on the previous ones. So it gives you a kind of recursive procedure for solving this equation. Okay? And you can write what the solution should be, and what you see is that the solution gives you all the elements of this set by increasing size. So this is like the generative process that produces all the elements of this set, just assembled into this simple fixed point equation. So why do I want to write it like this? Oops. Suspense. Okay, so why do I want to write it like this? Well, because this kind of way of expressing generative processes in terms of this type of fixed point equation and recursive procedure is actually the way that in physics one writes these solutions of the least action principle, which are called Dyson-Schwinger equations for quantum. It's a typical thing in quantum field theory. You want to know what in classical physics would be exactly the solutions that satisfy the least action principle. When you want to implement them in quantum physics, you have this recursive procedure over the contribution of Feynman graphs of increasing size. And the way that you check the contribution by increasing size is exactly this type of fixed point equation. So it's common thing to describe this type of generative processes in terms of a recursive fixed point equation. So that's just that. And it turns out that the one that describes the syntactic merge, which is this one, is the most basic one of all these possible Dyson-Schwinger equations. So you have a characterization of this core computational process of syntax that Chomsky describes in his paper as the most fundamental example of this class of equation versions with equations. Okay, so now a little bit more structure, right? Because so far what I described here is just this formal backbone computational structure. But as I said, here I'm just not, I'm leaving this kind of empty variable x attached to all the leaves of the tree. So I'm not specifying anything here. Now we try to input a little bit more, that makes it more, more linguistically interesting. So so this is what Noam calls syntactic objects in papers. So you do the same thing. So this the same kind of magma with this merge operation. It's an associative commutative magma, but now instead of having this single variable x, it's the non-associative commutative magma on a certain set, and this set is the set of lexical items and syntactic features. And so what this means is that you are again constructing considering so the elements of this magma are again these binary rooted trees with no specified planar embedding, but now the leaves of these trees are decorated by elements in this set of syntactic features and lexical items. And so I'm just going to put this here. It's this is kind of just a formal trick again. I'm adding to this set a kind of empty tree object, which would just have the property of being the unit with respect to this operation. Okay, so if you merge a tree with an empty tree, it just stays the same tree. That's okay. So here's again the equivalent description that I said. Okay, and these binary rooted trees with the leaves decorated by the element of the set, and the operation is again this merging of trees with a common root. So, okay, these are the syntactic objects. Then what Chomsky introduces in his papers is workspaces and the action of merge on workspaces. So the idea of what these workspaces represent is that they are the kind of material that's available to you for structure formation. So as you are in the process of composing a sentence, you have these pieces that you can use to build sentences or to modify sentences. And so this is the material that's available. And so each step in your derivation is an operation on these workspaces, on the workspace that you have available, that produces a new workspace, and then the next step will produce a new workspace, and so on. And okay, there's some, so this says that there should be some rules about what these transformations of workspaces should do, so that your derivation kind of converges to some final output, and also does not lose information, so that things that you have used remain available for future modification. So you can kind of write down a list of desired properties that your successive modification of workspaces should do. And that's how the action of merge on workspaces can be characterized by kind of a sort of axiomatic characterization in terms of what are the desirable property from the point of view of linguistic formational structure. Okay, so what does, I'm going to give you directly what the corresponding translation into the mathematical formulation looks like. So from the mathematical point of view, workspaces are forests. So forests are just a disjoint union of trees. So it's like a collection of trees. Again, not with no particular ordering. So no, it doesn't matter in which order they come out. It's just so that you can think of it as a disjoint union of trees. And so each tree is a syntactic object. So it means that you have a bunch of syntactic objects. It's better not to consider it a set, because you can have repetitions, right? You can have the same syntactic object that plays different roles in your derivation. So there's an important distinction that usually Chomsky does make in his papers, which is this distinction between copies and repetitions, and the copies are really the same identical object that in the course of a derivation you kind of, for example, when you do internal merge, you kind of double the same, and then you cancel the deeper copy. But the repetitions are not copies; they are actually can play different roles in the same. So in this sense, this is, well, you could say it's a multi-set of trees, but we could just say it's a forest. That's and yeah. So the set of all possible workspaces is the set of binary rooted forest. The rooted forest, I mean that each component tree has a root, and again with no assigned planar structure. And so what the thing that you can say is that the material that's available for manipulation, for computation, structure formation in a workspace is whatever you have already obtained through previous application of purge. And so there's a kind of inductive definition of what is available. And so the way to formalize that notion is through this notion that introduces of accessible terms. So let me say in this language what accessible terms correspond to. So you can think of it this way: if you have a syntactic object, which is a tree, with the leaves decorated by lexical items. So if you take a vertex in the tree, you can look at everything that's hanging below that vertex. So that gives you a certain subtree, and not some subtree of particular type, which just catches everything below that vertex. And so if you look at all the ones that are not the entire tree, so you take any vertex that's a non-root vertex, and you look at everything below that, then that's an accessible term. So the list of accessible terms are in a bijective corresponding with the list of vertices that are not the root. And also if you have a forest, then you define the set of accessible terms of the forest as being the union of the set of accessible terms of each tree in the forest. So now the thing is, there's a bit more structure here around this notion of accessible terms, and this is where this concept of Hopf algebra comes in. So this set of workspaces, which is this set of binary rooted forests, is actually it's not just a set, it has some additional structure, which is this Hopf algebra structure. So what is a Hopf algebra? Okay, I'm going to give you the formal definition in a moment, but the important thing is, what does it mean? Right? So what it means is that you want to keep track of two types of operation. One is sort of an operation that puts things together, and one is an operation that pulls them apart. And there has to be some compatibility with how you put things together and how you pull them apart. So the way to formulate that is that there's a product operation, which is like your assemble operation. So a product has two inputs and one output. The two inputs are the two things that you want to put together, and your output is the result of putting them together. And there's a coproduct that does the opposite thing. It sort of splits things into pieces. And it is so these two operations sort of dual to each other, but there's one difference, that usually if I give you two things, there's one result of what it means to put them together. But if I have one thing, there's usually many different ways in which I can pull it apart. And so that's again where I use this trick of writing all the possibilities together as a sum. So I produce in a single step. So this coproduct will produce in a single step the entire set of all possibilities of decomposing your object, and just show them to you in the form of a sum. Okay, so then you can make this precise, right? So you start with some vector space, you have a multiplication operation, a co-multiplication, so you're putting things together, pulling them apart. You say, two inputs, one output, one input, two outputs. You have like a unit, like this thing that doesn't do anything under multiplication, and you have a co-unit that doesn't do anything under co-multiplication, and you have an antipode, which is kind of the way to relate the duality between these two structures, the compatibility between multiplication and co-multiplication. And they have to have a list of compatibility properties, which can all be expressed in terms of some. I'll just show you in a moment. That is, so they tell you how these constraints are sort of telling you that you choose these two operations in a good way that are compatible with each other, so that they are compatible with each other. So the formal way to describe these properties in terms of these diagrams, multiplication is associative, means I multiply these two and then I multiply with the other one, or I multiply these two and then I multiply with the other one, and this will be the same thing. And unit is multiply with the unit on one side or on the other, and the result is the same. So that stays the same. And the co-multiplication is just the same, but you reverse the direction of all the arrows. So it's kind of simple to represent these properties in this graphical form, but they simply, and then there's this operation that tells you that multiplication and co-multiplication, unit and co-unit are compatible with each other. So that and this operation of compatibility, this antipode, as there's a good thing, which is that if you have a grading on your algebra, which is in our case is this thing I was saying, that you can just keep track of the length of sentences, then the construction of this compatibility actually comes for free, because it's done inductively on the. So this simply means that you can check compatibility between these operations of pulling things apart and putting them together. You can check it inductively by degrees, and you can sort of make it so that they become compatible inductively by degrees. Okay. So this is what a Hopf algebra is in general. And this is a structure that is kind of ubiquitous in mathematics whenever you have combinatorial type of structures, because it's exactly with combinatorial structures, you normally want to know ways of composing and decomposing objects. And so this is like the most natural algebraic structure that keeps this the composition properties together. So it's like a very, very natural language to use whenever you have in a situation that has this type of flavor. And so so what about the Hopf algebra structure on workspaces? So workspaces are, again, these collections of trees, collection of syntactic objects. And the product operation is very simple. You have two sub-collections. You make a single collection with both of them at the same time. So it's like you join together your two different workspaces into the same one. Right? And as I said, this unit is just this empty tree. If I add an empty thing, then I'm not changing anything. So that's it. The coproduct is where the interesting things happen. And so the coproduct is exactly where you keep track of this idea that you have accessible terms. You don't have just the syntactic objects in your workspaces, but you can search inside your syntactic objects for pieces that were coming from previous. The syntactic objects themselves are constructed by this magma that keeps applying this merge operation trees. So inside the bigger tree, you keep track of all the previous ones that you have constructed in the process of getting bigger ones. And so this is where the coproduct decomposes things and allows you to see the smaller pieces inside the bigger one. Okay. So the coproduct is exactly doing this. So it extracts a sub-piece, which is what, so it extracts an accessible terms and cancels the deeper copy of that accessible term. So on one side, you decide which accessible term you want to use, you take it out, but now you don't want to keep another copy. So this is an actual copy, it's not a repetition. So you don't want to keep another copy of it. So the deeper copy that was down in the tree, you cancel it. This is exactly what you do normally when you do internal merge, right? So this is designed so that you have that operation available. And of course, there's many accessible terms that you can access. And so the coproduct lists all of them as a sum. Okay. So that's the structure. There's one small subtlety here that when I want to describe how you make this cancellation of the deeper copy of my accessible term, in principle, I have two ways that I could do that. So imagine that this is the tree that I start with, and that this is like the accessible term that I want to extract. And now I want to cancel this deeper copy of the accessible term. So one way that I could do that is to say, I just shrink this tree just to this node. And so these two leaves become a single new leaf here. This is this contraction property. So I'm left with the rest of the tree here, but these two just contracted here. I have another thing that I can do, which is I can just delete this tree entirely. And then I also, so I remove it entirely here. And now there is so I have to say what I'm going to do with this. This node here is no longer relevant because there's nothing branching there. So I can just eliminate this node and just take this. Okay. So which one is preferable given what I want to do with this? So I'm claiming that this one is preferable. Why? Because if I want to do this, now I have to assign a label. This one is now a leaf. So it was an internal node before. So I need to assign a label to that now. So now I need a kind of calculus of labels to the internal edges, which of course in the older version of minimalism you would do, because you look for the head, okay, and you label the internal vertex with the head of that. But in the new one of the aspects of the new version of minimalism that Chomsky said is that all these aspects should go into the later externalization phase. You don't want them to be part of the core computational structure. If you do this, you have no need for labeling of the internal vertices. You just keep the labels only on the leaves. So that's why I think this is the version that you want to use here to canceling the. But there's some slight differences computationally, and in fact, I was first trying to write it in this form, and then I realized that actually maybe this is a more convenient way to do that. Also, there's another difference that if you happen to take as the accessible term the entire tree, which is what you do when you do external merge, right? Then what would be this quotient? Well, if you do this, it would be just a single root vertex to which again you have to assign a label. But if you do this, then it would be just this empty tree. And I think again it's better. It works better if you think of it this way. Okay. So so this is what I mean by the cancellation of the deeper copy. And again, then one can show that this coproduct defined in this way. So now the coproduct extracts. So you can extract one accessible term, or you can extract a bunch of accessible terms. So you have this coproduct that lists all the possibilities, and this has all the good properties. I mean, all this associativity, co-associativity, and compatibility between the product and coproduct structure. So with these operations, this set of workspaces is a Hopf algebra with all the correct properties. And now there's one thing that it's convenient to look at, which is some form of keeping track of the size of the workspace. This is for the reason that I was saying that you would like to keep track of the fact that as you keep applying the derivations, applying the action of merge on workspaces, you want your derivation to converge to something. So you would like, for example, the size of the workspace not to keep increasing. We would like it to be either stay the same or decrease. But also, you don't want to lose access to syntactic information in the future operations. So you want the number of accessible terms to not decrease, so it could stay the same or increase. So you can put some constraints on some. So you can introduce various sizes, counting of sizes. So one simple counting of sizes is the number of syntactic objects that you have in your workspace, so the number of connected components of your forest. Another is the number of accessible terms in the entire workspace, or a combination of the two. So the total number of vertices is the sum of these two. And this one looks a little bit strange because I'm adding one more time the number of components. but I'll show that this actually is a nice number because it's actually a conserved quantity in a lot of good, part of merge. And you also have this grading of the Hoffager by number of these. So you have a certain number of quantities that you can keep track of as the merge Jackson workspaces. So I haven't yet told you how merge Jackson workspaces. I've only told you what the workspaces are. So let me. So far, I mean, this off-algebra structure is only based on these, assembling together workspaces and extracting and accessible terms from workspaces. Now I want to define the actual merge on this set of workspaces. So I'm going to write it out as a formula, and then I'll explain what this means. So you can write it as a, let me write it like this, and then if you look over all possible syntactic objects, you can write it in a more concise form like this. But let me say I choose two syntactic objects, and I want to use those to make some structure formation on the basis of the workspace that I have. So I can then describe the action of merge for this choice of syntactic object on the workspace in terms. So this uses all these operations that I have in the Hopf algebra, but it's not an algebra or coalgebra morphism. It just uses these operations. Okay, and so it uses the coproduct. It uses this. I kind of glimpsed over that quickly, and I didn't say much before. Let me just fly back to one of the earlier slides. I'll come back in a second, but I just wanted to show you where this appeared because, yeah, here we are. I only mentioned in general that these Dyson-Schwinger equations in physics are some kind of fixed point equation, and there's a certain operations which I call this B. And this is exactly the one that defines the action of merge on workspaces. And now I'll describe what it is. Here I just gave it a name, but it's the same one that occurs here. So this is the operation that takes a forest, so a union of disjoint union of trees, places a root somewhere and attaches all of these to the same root. So it can be n-ary if I have n3, it can be binary if I have 2. In this case, it's going to be binary, but it would be the same operation that if you had an hypothetical n-ary merge, it would do it with n, but no, in this case, it doesn't. So this is this operation that grafts together the components to a single tree, and this is the product, so the one that puts together pieces into a single new workspace. Okay, so I'm gonna go make it more explicit. So in particular, okay, if you want to look at the action for over all possible choices of syntactic objects, then you have this simple form here: coproduct, this grafting operation B, and product. Okay, let's unpack a little bit what this means in a more explicit form. So this is a composition, so you start reading it from this side. So you hit an object first with this, then with the other ones. So the first thing that you take a forest in the workspace, so your forest that defines your given workspace, and first hit it with the coproduct. So it means that you are looking at the list of all the possible accessible terms of that workspace. That's what the coproduct does for you. It kind of presents to you the list of all the accessible terms of that workspace and cancels all the copies of them. Then you search whether your desired syntactic objects are there or not. If they're not there, then this merge operation is not doing anything because it has nothing to act on. So it means that if they're not there, you just leave the workspace unchanged. If they are there, then you apply this dumping operation. So you take the terms that you find and you put them together in a single tree and leave everything else unchanged. And then this assembles everything back together into giving you the new workspace. So that's the steps of what this action of merge on workspaces does. and it takes the workspace that you have and produces a new workspace. Oh, okay, as it happens often in this business of merge, one at first gets worried about the fact that maybe there are too many different types of merge involved in this operation. And indeed, if one just writes it like this, there are. Because, okay, this is the modified part of the workspace that you see. I say these were like a priori two different components, but maybe possibly the same one in the workspace, where you're accessing a particular accessible term of this one and a particular accessible term of this other one. Those are the ones that you use to assemble a new tree, and these are the cancelled copies. So the new the modified part of the new workspace, so whatever else that you have not used stays the same, but the modified part looks like this. And now you can see that there are various cases, depending on whether these are the entire component, that could be the external merge, or whether it's one component and an accessible term of the same component, and this would be the internal merge. But then you can see that you also have other possibilities where this would be two accessible terms deeper down into different components, or so you have this other, or something inside. So one component and something inside another component. So you have this other form of either sideward merge or countercyclic merge that in principle you're also getting. So why is this something that you should worry about? Because this type of forms of merge, this type of sideward merge and a countercyclic merge have undesirable linguistic properties. So you can get examples of things that are not syntactically valid that are produced by this type of merge operation. So in principle, I would like to be able to only keep these two cases, which are the good type of merge. Okay. So let me make before I continue with how to do this, let me make a comment. So I have thrown in this empty tree, which has this property of being stationary. Let me just make this this small remark. That the internal merge, this is something that also observed in one of his papers, that the internal merge has almost the same structure as the successor function of piano arithmetic. But language does not contain arithmetic. And one way to see that is that the first step of the piano arithmetic would require also a unary merge. And after that, it's all the internal merge, the binary internal merge. But with syntactic objects, it's not quite the way it works. If you take the merge with the empty set, it's the unit of that. So it's similar to the successor function of piano arithmetic, but it does not contain a copy of piano arithmetic. Okay, but I'm going to make this comment here that way to see in this setting internal merge, you can view it as a formal. This is just a formal trick, so you shouldn't read too much into this in terms of meaning. But it's just that formally, the internal merge, you can think of it as an application of merge with one of the syntactic objects is this empty one, and that simply produces a new workspace where you have made your accessible term that you want to use one of the components, and you have made the corresponding cancellation another component, and then external merge puts them together. So in this sense, it's like saying that internal merge is external merge applied to this pair of syntactic objects. But one is this after a merge on this pair of syntactic objects, one is the empty tree. But I mean, one can see that this one really doesn't exist in isolation. It only exists in these compositions that give rise to internal merge. And one reason is that it violates these requirements on size of workspaces. I'll say something in a moment about that. So it's just in a sense a formal way of describing internal merge. Okay. So now how do you extract the good merge, external and internal merges, and kind of get rid of the bad guys, the sideward and countercyclic merge? And so usually the way that this is done in the linguistics literature is to say that there's a minimal search type of argument that rules out these other possibilities. And the idea behind that is to say, okay, if you're looking for the material to use for your merge operation on the workspace, you first look at the top. So you first look whether there are two components that you can merge together, and that would give you external merge. And if you don't find two components like that, and you find only one of them, then you start to search inside that one for another matching piece, and you form internal merge. And all the other searches would be less or more cumbersome or less than this one. And so the question is, how do you actually formalize this in more precisely in terms of the structure that I described? And because in some sense you want to say, okay, if you want to call this minimal search, I'm going to kind of say minimal with respect to what? What are you minimizing? Is there some kind of cost function that really these two types of searches minimize, but the others don't? Right? That's the question. And in a sense, why is this a question? Well, I mean, let me give you this example, right? Suppose that this is your workspace. It only has two components. And one of them looks like this, and the other one looks like this. And now I'm trying to do this merge function, and one of the objects that I'm looking for to use as a merge is this entire component here. And now I want to say that when I look for the other one, it should be according to the usual minimal search, right? I want to argue that it should be easier to find this one than to find this one. This is a little unconvincing, right, at first, because to find this one, I have to go very deep into this tree. Whereas this one is very close to the root into the other component. So I need to choose my sort of cost function very carefully if I want to convince you that finding this one is easier than finding this one. Okay. So, all right. So how are we going to do that? Well, so here's the idea. Extracting this workspace, extracting these accessible terms from the workspace is what the coproduct does. That's what we have decided. Right? That's this algebra structure is exactly doing this, extracting accessible terms. So now we want to weight this extraction in such a way that certain extractions are more costly than other ones. So I'm going to put. So I have two terms in the coproduct, right? Because coproduct has two outputs. I can put a weight on both of them. And then I have to adjust how I put these weights so that my minimal search is actually minimal. So I'm going to put a weight to the part that I extract, and I'm going to put a weight to the part that remains, the one with the cancellation of the deeper copy. And well, one reasonable way to think about how to weight it is, so I'm trying to argue that where my accessible term lives is important. So how deep I'm going. Okay? So I kind of try to weight it by how deep I have to go. So I put in each accessible. So here I can extract in the coproduct. I can also extract multiple accessible terms. So each one of them, I look at how far down it is from the root. I weight it by how far down it is from the root. And now what I can say is that okay, I put this so that they complement each other. Right? So it's more difficult to extract things that are very far down from the root, but it's more difficult to cancel things that are very close to the root because I have to cancel a very big thing. Whereas otherwise I have to cancel something that's very deep down. So that I have a cost of extracting something, I have a cost of canceling the copy. And these two costs has to somehow balance one another for the search to be the optimal one. And so I can do that by introducing this grading, and then I take the leading term with respect to this expansion when this parameter goes to 0, which means I search for the terms in which these two costs balance each other. And that exactly gives me external and internal merge. So that's a characterization of in what sense external and internal merge are actually optimal in this setting. Okay? They balance the cost of extraction and deletion of the copy. Okay, so as one knows from the literature in linguistics, there is this minimal search argument for why external and internal merge are the ones that you want to keep and not the other ones. Okay, we have set that. We have settled that. But there is also usually an argument that is made, which is in terms of what happens to the size of the workspace. So you can rule out certain types of merge by saying that they violate some reasonable rules about how the size of the workspaces should behave. And so we can see that this also works in this setting. So, externally, so I put down a bunch of different ways of measuring the size of the workspace. So this is the number of connected components, the number of accessible terms, the sum of the two, so the number of vertices, and this additional that again adds the number of connected components. Okay? So external and internal merge. So what I'm writing here is by how much it changes when you apply. So this means that when I apply external merge, I'm decreasing the number of syntactic objects by 1. I am increasing the number of accessible terms by 2, because the two roots become 2 internal vertices. Right? I am increasing the overall size of the workspace by 1, and this is a conserved quantity. In the case of internal merge, everything is conserved. Well, this is kind of clear, right? Because internal merge is really manipulating the form of a sentence. Is not, so it's kind of reasonable to expect that all of this will actually be preserved quantity. And what about the other forms? So internal and external merge, this is how they behave. What about, one small comment, that for internal merge, the reason why this is a conserved quantity is because of the way that I'm taking this cancellation. And I told you there are these two possibilities, and I chose the one with the deletion rather than the one that contracts. And for this reason, I have that the total number of accessible terms that I start with get distributed over the part that I extract and the part where the deletion happens, but with a change of 2. And this is because of this. Let me just come back to the picture, right? It's because of this, because you have this vertex that disappears, and this one disappears too. So that's the change of 2 in the number of accessible terms. And this counting is actually consistent with the one that is used, for example, by Bob and Sandra in this setting. So that is kind of on the same page with this counting of size. So here's the reason why I said that when I want to write, I use this trick of writing internal merge as external merge applied to this other sort of weird merge with the empty set. And I said this doesn't exist by itself in isolation. It only exists when it forms internal merge. And the reason why it doesn't exist in isolation is because it violates all the good properties. I mean, it would kill accessible terms, and you would reduce size of the workspace. So the overall size, not just number. So it decreases number of syntactic objects, which also is also bad. You want the number of syntactic objects to decrease. So it's bad on all counts. So it doesn't exist by itself in isolation. But when it forms internal, it becomes a part of forming internal merge, and then it's okay because internal merge is fine. And in the sideward counter-cyclic merge, they all violate something. So they are also ruled out on the basis of these countings of size. So you can kind of summarize the whole thing like this, that the desirable property would be that the number of accessible terms is known decreasing, the number of syntactic objects is known increasing, and the size of the workspaces is not decreasing and not increasing more than 1. This is also one of the conditions that you find sometimes listed in the literature. And I also throw in this additional condition that this is a preserved quantity. Okay, and if you see, because if you look at these various conditions, you see that okay, internal and external merge are fine with all of these, but no single one of them rules out all the others. But for example, if you take this one plus any of the other ones, it's enough to rule out any. So a combination of these requirements will rule out all the other merges, the known good ones. So I want to come back to this thing that there is this thing that at first it makes you think that this, if you do this cancellation by contraction instead of by deleting this piece, it would, in a sense, be nicer. And this is this observation that if you do that, then internal and external merge would be the only ones that increase the number of accessible terms exactly by 1. But okay, so that would make it look, but for the other reasons that I said, I think it's actually more convenient to take this cancellation of copy as deletion rather than as contraction. You don't have to worry about this labeling of internal vertices and so on. So, but still, you can see that these properties are enough to rule out all the bad guys. Plus, you can rule them out with this minimal search argument that I explained it. Okay, so okay, let me. So I have a bunch of material of various kinds in the slides, which I will not cover, in the lecture, and I will distribute the slides so you can there. So one thing that I can say is this thing of why you don't have a merge that's n-ary with a arity that's 3 or higher. And that you can see both the under generation and the over generation. But maybe maybe what I can say something about quickly, I can skip this part and I'll leave it to the slides. But one thing that I can say something about quickly is the externalization part. And I'll try to, it's again a little bit of an involved story, but I'll try to make it quick. So yeah, okay. So of course there is this thing that up to now all the structures that we've seen are completely independent of planar embeddings, which means that they really only see the combinatorial structure of the trees. They don't see the linear ordering. There's nothing about linear ordering. So there's nothing about word orders or things like this. However, we do know that language, the way that we use it, because of the way that speech is generated, is necessarily forced to go through this type of linearization process, is called linguistic, or maybe I call it planarization, which means that you are forced at some point to fix a planar structure of the tree. So that fixing a planar embedding of the tree is the same thing as fixing an ordering of the leaves. So it actually does create a linear ordering in your sentences. And of course, this is where also things become language dependent, because the way that this ordering works is dependent on syntactic parameters of particular languages. And so in this point of view, there's so all the merge computation take place before this happens, and then you assign planar structure. This is where there's a main distinction between this formulation of minimalism and the older formulation of minimalism, where you directly describe the merge operations on the planar trees. And this, again, there's a bunch of material that I've added in the slides that I will not talk about, but it's in our second paper, that you can see that if you do that, then you run into a much more complicated mathematical structure, because you have to keep track of this fact that the trees are planar, and the combinatorics of these off-algebra combinatorics become more complicated for planar trees. And also these internal and external merge is necessarily going to have some not be defined on everything, and has some specific domains that depend on labeling, like heads of trees and so on. And so you end up with all these partially defined operations, which makes the overall structure much more complicated. The reason why this is happening is actually very simple, namely, when you do this kind of free symmetric merge, as Chomsky calls it, which is the one that I've been describing, where the trees are non-planar. Then you have these non-associative commutative magma, where in commutative, because exactly you can flip all the possible planar embeddings of the tree, and they're all equivalent. You could also work with planar trees, and then you have this non-associative, non-commutative merge, because now, if you embed the tree this way or that way, it's two different trees. It's no longer the same one. And you have all these planar trees, but the thing is that you do have a morphism compatible with this operation of composing trees together, this merge operation, that goes from the non-commutative one to the commutative one, where you just forget about the planar structure and you identified all the ones that are just different planarization of the same tree. But you cannot go the other way around. No, you don't have any morphism compatible with the operation that would go from the commutative to the non-commutative one. Because the only way that you can map a commutative operation to a non-commutative one, if it lands in a sub part that is it's already commutative, but you cannot have any part that's already commutative so no non-trivial submagma is commutative in here. So you cannot climb this map, this projection, in a way that's compatible with merge. So you either have all the merge happening before externalization, like in this formulation, right? And then externalization is a section of this projection, but it's a section that's not compatible with the merge operation. Or you can try to write to your merge operation after, which is what the previous, all the formalism of minimalism are doing. But then you have problem because all these are only partially defined, precisely because this map is not a morphism of magmas. Okay, so you're paying a price for the fact that you're trying to take a one-way street the opposite way. And okay, so maybe I should just let me skip part of the structure here, which is interesting, but I don't have time to talk about it. But I want to make one final comment, which is that there are kind of competing proposals to externalization. One of them is this type of linearization algorithm, like Kane LCA, and which essentially propose that there is a canonical choice of a planar structure. Okay, from a mathematician point of view, we say that's not possible. I mean, you don't have a canonical choice of a planar structure for trees. But of course, this assumes that there's additional information on these trees, and the additional information is the concept of head in the syntactic trees. And so you follow the head of the tree, and that gives you a choice of planarization. But I mean, the point is that if you want to use that instead of externalization, you would like to be able to apply this to all the syntactic objects that are generated by the free merge. And the problem is that there's no way to have a well-defined head function on this entire magma of the generated by the free merge. And this, you can just see it very simply in this way. Like if I'm doing external merge, I know what the head of this tree is, and I know what the head of this tree is. And when I do external merge, I have to decide whether the head of the new tree goes that way or goes that way. So I have like two choices. And in principle, I would like to be able to assign such a head function only on the basis of the labels that I have at the leaves. So the basis of the lexical items. Well, that's how you normally decide where the head of the tree is, how you mark the internal vertex. But now, even if under the strongest conditions that this set of lexical items is a totally ordered set, I would still have a problem because in principle, my two trees could have the head labeled by the same label. I cannot rule that out. And then I have absolutely no way to say that the head should go this way or the head should go that way. So the point is that you cannot use something like the LCA as a replacement for externalization, because it simply would not be defined on the entire. So you're again introducing domains and partially defined structures, which is what you expect, because it's the same. It would be the same as doing merge after planarization, and it's not well defined everywhere. It's only defined on subdomains, and you kind of introduce a lot of complications in doing that. So in a sense, this is like a very simple mathematical proof of the fact that this new formulation of minimalism is indeed preferable for in terms of simplicity of structure with respect to the older formulation. So I'm going to stop here. There's other stuff in the slides, and I'll make them available to everybody. So yeah.
Very much. It's time for questions. People online, if you want to ask questions, raise your hand and we will let you talk. And here really means is take them. Questions. You don't need to moderate, right? So I think the first question is here. You shouldn't talk. You're my husband. He shouldn't be allowed to talk.
I'm just pretty.
Go ahead.
No, I was so that it's. I think it's what some of the slides you've skipped. So
there's many.
so I can ask it, right? So also you mentioned now the intriguing parallel to the Dyson-Stringer equations. And then, so I saw there were slides.
Let me go to the slide I skipped. So that
what do you think this means? So is it just a fun parallel? Is it?
No, I think it's actually a useful one in the sense. So yeah. So one way in which is useful is this thing that it's while it shows in some sense that this merge is optimal in the same sense as these solutions of Dyson-Stringer equations are optimal, which is so. Physicists realize that when you try to in this quantum setting, you try to describe what your least action. In classical physics, the equations of motions are the ones that satisfy the minimal energy requirement.
Right.
So they are optimal in that sense. When you go to quantum physics, just stating it that way doesn't quite work, because in quantum physics you can sum over all possibilities, over all paths. So also the ones that are not energy minimizing are contributing. So in what sense are solutions optimal in the least action sense? And at some point, we realized that the way to do that is to actually separate out this optimization into two parts. One is like a combinatorial part of the optimization, and another is the evaluation on the result of this combinatorial solution of the action. And if you do that, it's equivalent to this least action principle in classical physics. And this combinatorial part is exactly the solution of this fixed point equation. This combinatorial doesn't matter. So it's a way of saying that there is a way of describing this least action in combinatorial terms. And so you can think of this as like a justification of in what sense merge is optimal.
So it's an optimal way of optimizing.
Yeah, it's like, because in several places, like if you read some of these recent papers of Chomsky, he's saying that okay, merge should be in a sense this satisfy some kind of optimal simplicity type of it. So, but in what sense? So this is the sense in which it does satisfy this optimal simplicity in the same way as these Dyson-Stringer equations satisfy this action. Okay, but this is kind of an interpretive type of thing you can get out of this parallel. I think that it's useful for other reasons, because another role that this plays in physics is the fact that in physics people run into this problem that when you try to compute these expectation values for processes and in quantum fields, you run into a lot of you have this problem of how to extract the meaningful part. Because the problem is mostly these type of Feynman diagrams calculations give you meaningless
infinities, meaningless diagonals, and you have to get rid of those and extract the meaningful part. This is what physicists call renormalization. And again, this has a very nice combinatorial description in terms of this off-Hauser structure. And so one thing that's never discussed in what I said here, which is purely about the computational aspect of syntax, is that you also have an interface between syntax and semantics. Right? When you do parsing, so you can rule out certain trees purely on the basis of syntax, but you can rule out others on the basis of semantics. So at some point you have to pass through, there's this externalization process, but there's also another thing, which is the syntactic semantic interface that you have to model in some form. And this has to be also, everything, if it has something that happens inside our brain, is some kind of computational process of some form, because that's what our brain does. So there has to be a kind of computational process that accounts for this semantic syntactic interface. And one way you can think of what this does is something similar is the extraction of the meaningful part. Right? You want to throw away things that are the meaningless ones and keep the ones that are the meaningful part. So it's very similar in structure to this thing that happens in physics, where you try to extract the meaningful part of this Feynman diagram calculation and throw away the bad part. So I think, in a sense, this analogy is proposing a way of modeling the computational structure of the syntactic semantic interface. And I think that is where it's actually helpful in a more direct way.
Yeah, so thank you for your very interesting talk. So I have a small question, because there is this other concept of merge, which you didn't mention, but which pops up in Chomsky's speakers now and then, namely pair merge. And I want to ask him, can you explain it to me? And he did, but still sort of, I need to completely follow him. But if I understand it correctly, sort of, pair merge, there is an ordered relationship, right? No, okay. So I see you're really sort of saying, no, but so what intrigues me is this. Okay, so I think he sort of assigns sort of pair merge to, let's say, the generation of adjuncts in a bigger structure, right? So he has a particular set of objects in mind for sort of using, sort of, integrating sort of, adjuncts into the structure. So my question was always, okay, why do we need sort of, this extra sort of, type of merge, right? Why is not sort of, set merge sufficient, right? And sort of, how does this relate sort of to the sort of final part where we discuss the LCA, where there is a connection, let's say, between hierarchical structure and linear order, right? Which you seem to have also in pair merge. Right, so I'm just curious. So what your
Okay,
thoughts
so
are
I have to say that I have not thought about that. So I don't know how to do that, because it's not, I haven't thought about it. But so of course there's some things you can do, in the sense that, for example, so far the only structure that I'm putting on trees is labels of the leaves, right? And so the leaves are marked by lexical items and syntactic categories, but I'm not adding any. For example, I'm not adding any labeling of internal vertices, which you normally do in the older combination using. But for example, one could do versions of this type of algebras of keys and where you also keep track of certain ways of labeling internal vertices. So you get you can construct versions where you put additional structures on it. And you try to keep track of that structure through the various operations that you define. So of course, then you say whether adding that structure makes things more complicated, it's helpful, it's not helpful, so that depends. But that, for example, in physics, when people do these calculations, so you have these Feynman graphs, and it's important how smaller graphs sit inside the larger graphs. So you can visualize that by trees. They tell you like how subgraphs are nested inside graphs, but these trees are decorated by the actual shapes of those subgraphs. So you have like this data, additional data on trees that you keep track of. So I haven't thought about it deeply, so I don't know if this is the right answer, but one thing we can do to accommodate other is to think in terms of adding structure to the trees, in terms of labeling of internal vertices with rules. Like, okay, in the second paper, we look at some of the formulation of minimalism, like for example, Stabler's computational minimalism, but uses this internal labeling where you just follow the direction of the head of the tree, and then your merge operations keep track of the labeling of the heads and how you apply them only if you have certain matching structure in labels. And that gives you a slightly different type of algebra structure. And you can see that, okay, everything still makes sense in this language of algebra, but it becomes a kind of very more complicated stuff. So in some sense, you can say, okay, is this additional complication really necessary or not? So the way I would do about like comparing other is to like see how the underlying mathematical structure changes if you want to keep track of additional data, and then see whether this change is making things more complicated or how to compare that.
Well, so because it intrigues me, because the objects, let's say adjuncts, can be of the same categorical types as arguments, where they can be PPs or NPs or whatever, right? So as sort of formal objects, they're not really different, let's say, from argumental objects that are more intrinsically related to verb, right? So if you approach it as purely sort of geometric sort of configuration, the question arises, okay, but why need, right?
Yeah.
A different kind of sort of, combinatorial operation that sort of, brings, let's say, verbs and objects together and verbs and adjuncts, unless you assume that looks in the syntax semantics interface, right? The structure building process, right, feeds sort of interpretation that you say, okay, you automatically know that sort of an adjunct interpretation if sort of parent merge is going on. I'm always intrigued because adjuncts in the way are more versatile in the root order behavior. Look at it, John left the room quickly and John quickly left the room. Then sort of many arguments, right? And so that always puzzles me a little bit, and because pair merge itself is sort of an ordering relation. But I see. So maybe Irina can see more about it. I was curious about your collaboration with Chomsky, the way you discussed the pair merge.
Yeah, no. So one thing that I think is actually that. So this is actually what we're hoping to next, which is this syntactic semantic interface in terms of that physically modeled on what happens in physics in terms of this separating out the meaningful part. And I think things like that will probably fit into that type of interface.
Well, I think you gave the solution itself. Pair merge cannot be a primitive option. I mean, it violates merge theory. So what is it? Well, maybe you might say that that you generate a number of steps in the workspace, and since these adjuncts do not involve, let's say, are not involved in predicate argument structure or in theta theory, you're left with a bunch of these things, and when you can connect them to the objects that are generated and which satisfy data structure, then you could have a visual interpretation. And in fact, another way, of course, looking at it is we're saying that these admin structures are actually added dimensionalities. So you have a basic structures, and you have a bunch of these other stuff, and then we are in another dimension with at the same level, and then what we're saying, different orderings are just externalization. And no one knows exactly how it is. It's not a trivial problem, but it solves conceptual.
Yeah, I know, but I'm not satisfied. But syntactically, because you can see that morphosyntactically, post-verbal adverbs behave differently. So you can say John left quick. John quick. And so morphosyntactically, can see that whether it's pre-verbal or post-verbal has sort of more syntactic consequences, which you wouldn't expect if it's only memorization. Furthermore, and that's still also what I liked about the old days, was that you know you had well, the subject and adjunct sort of behave similarly, but there will be for that too. As far as sub-extraction, right? There was one observation that conditional extraction domains are subjects and adjuncts sort of behave similarly, and sort of sub-extraction from those domains. And now that's really your own story about it too, right? I mean, so they should have different sort of explanations, right? Even though their behavior is sort of symmetric, right? You can't expect it. There are some examples.
Give an example of something.
Oh, so
Yeah.
So sub-extraction is where who did you see a picture of, right? You extract. So you have the picture of who, right? And then you extract who. Did you see a picture of? You extract it out of the dialogue. And who was a picture of seen by everyone is out in English, right? Because they're a picture of John, right? Because you have a passive construction, picture of John was seen by everyone. Then you extract the picture who out of the picture of. Right? And when it's a subject, you cannot extract. So you can extract out of object and subject. And so,
And the same goes for
and the same goes for adjuncts, yeah, so that's a bit more different. I said, John cried the day of my departure. Whose departure did John cry the day of?
Yeah, so one thing that I didn't have time to say, but you know, is that in the way one thinks about externalization, like it's really kind of a two-step process that I like to write it in this term that mathematicians call the correspondence, in the sense that you know often you're going to go like from place X to place Y, and instead of having a function that goes from X to Y, you sort of have like a two-step thing. One would actually not this way. So one is this thing of assigning a planar structure. And this is where I'm saying that you're climbing a map the wrong way, because you know normally the thing that's compatible with merge would go down, but you're trying to pick a section of that into the map. But then you still have to do something else, because in principle when you start with this pre-symmetric merge, you generate a lot of things because your labels at the leaves are a priori arbitrary. You are allowed to generate those possible keys. When you choose a planarization of the keys, all you want to do is be sure. So this is going to be language dependent, but you only constraint that you want to do is to be sure not to violate any of the syntactic parameters of that particular one. But still, you're going to have exactly the type of thing that you're saying, that a certain kind of will not necessarily be things that are then allowed in the language because of some other type of constraint. So the choice of planarization respects constraint about word order. Of course, you have other constraints. And then, so you have another markdown that sort of kills things that are not compatible with the other constraints. And there is where a lot of these things go. So that there's two steps of standardization. Not just, of course, it's not just choosing the planar structure, because then you will still have things that don't violate, like the examples you were saying, that they don't violate any word order rule, but you start, some of them still are not, syntactically viable. So that they still need to do that killing off all the other.
Yeah, well, I do think about the notion remove. Seems to me.
Okay, that's the question. So
Seems to me that is ambiguous in the sense that you can remove it literally. So in externalization, you don't see it anymore. And you can do it in a way that you make a formerly accessible term inaccessible. The way you also do that. So, because the terms made inaccessible remain in syntactic structure. Well, it's not important for this talk, but I mean, if you take in the semantics, it becomes important because they are interpreted in the semantics. John was seeing you have two copies, but the copy that really counts is the thing delete. But so it means that the notion remove should has two meanings. It's an externalization, but and there's also a different meaning in accessibility, and that leads to another stuff, another viewers. How do you find the minimal path? Take an object and you move down indefinitely far down to find another one, or we go to the workspace and find a member of the workspace. Syntactic options, and you are saying sound very convincing that if you look down in the same structure, you definitely down it's a lot of search, and that's true because your formalization is, as far as I can say, it's fine. It's to words, it's no problem there. But if you add another computational condition, let's say phase theory, then the search space becomes trivially small. Then,
sorry, how does it work?
No, well, so suppose let's say some categories are more important than others, and you can have a theory of that. So let's say you have VP, and you have C, you have a verb phrase, and you have a sentence. Let's assume that these are the two phasal categories. And then when you
Sorry, doesn't that require you to actually have assigned labels also to the internal data?
Yeah.
Because then you search by labels as well. So you are reintroducing the fact that you want to keep track of heads and things and assign labels to internal data.
Yes. Can I move to the first part of the
I think you've already asked the question, or
mine was formulated a little differently. I was confused about the terminology, whether you make a distinction between removal and cancellation. And I was wondering whether cancellation would still allow you to have something visible in the syntax, while removal would give you the option of still removing something, say in externalization.
No, there are two different things. So when I talk about the cancellation of the bit of copy of an internal merge, then you're not really, in truth, you're not really cancelling anything, right? Because the accessible term, you have taken it out, and it's still there. It's available for so you're only not creating. So you call it cancellation, but in fact, what you want to say is that you don't want to create another copy of it. You want to keep it, so everything remains accessible. So it's not like you're not really removing. You're not removing.
Okay, so but then
you are moving. You are moving something, but you're not removing something.
So you can keep it semantic interpretation.
Yeah, exactly. So it's still available.
And then the notion of removal is still reserved for the possibility of deleting a copy or parameterizing.
Yeah, so then there is another kind of removal, which is what happens at the end of externalization, where you say, okay, some of these things that I get now will violate some syntactic parameters. I kill those off. But the thing is that I will have the same, because I have the same material available in other things that are compatible. But again, not killing. It's just that some realization and externalization that might violate some syntactic parameters for that particular language, I need to eliminate that. But
I'm not getting it. The formalization that you gave the impression that it's not there anymore. So there is no copy.
Yeah. That's it. So that's the thing. You just want to essentially not creating a copy. You're moving your accessible term without leaving behind the copy.
For syntactic reasons, you might want to have a copy. What confuses me a little bit is that it formulate merge, or your merge
algebraic foundation. But now the linguistics or syntax needs something that is not in the formalization, because in the formalization there's no copy. But the linguists say that we need a copy for semantic reasons.
No, but it's still available. I mean, the accessible term is still available.
Yeah, but for, let's say, from
You mean for the
from
assignment of the
a
semantic
syntactic point of view, what is available is in some
Yeah, you want to
position.
have like a.
And you also
Yeah,
have,
okay. This was the reason why, in some sense, I sort of at first thought that you want to leave behind this, so you want to compact, leave behind this kind of new leaf vertex.
Yeah.
Yeah, like it would be like the phrase that you keep. So you can do that, but then, okay, you have to be careful about this labeling thing of what to do with that. So I agree that if you want to stress that point, you can do this. You can kind of leave behind this unit and keep it there for that purpose. And that, but of course, yeah, this becomes more relevant indeed when you want to think about the semantic, the sort of mapping to semantics, which for the moment we're not doing so. So for this part, you can say, just don't keep it there. But I think that you might want to do that and this, do this this contraction in this other way that leaves behind this marker.
but could we, if we move to the syntax semantics interface, then use, I forgot your word, that you basically unpack a little bit of the semantics from what you have, put it back.
So the thing is, so the way, so this is actually not yet really what sorted out. So I'm just giving you a kind of heuristic idea. But the thing is, this is based on this analogy with the physics setting. So you want to, so when you're trying to parse your syntactic tree and kind of have to map it to semantics, right? What it has is you can look at the subkeys, right? And you can look at possible effects, and you need that kind of compatibility, right? In the sense that your semantic should be compatible with, like if you start parsing pieces, you might have a priori different possible assignments, okay? But there has to be some compatibility with all the sub pieces so that they build together into something that maintains semantic coherence. And so this is very similar to what happens with this calculation in physics, where you have this subgraph inside common graph, and you start to extract the physically meaningful part, and a priori, because you go into increasing order size of the graph, you have already been dealing with the smaller graphs. So you kind of already know what should be the correct for the smaller graph, and when you re-encounter the smaller graph inside the larger one, your assignment has to be compatible with what it was in the smaller graph. It's kind of the same idea. You have to keep this compatibility with whatever you have already assigned to the smaller pieces, and you want to extract so that you can extract it simultaneously on all the effort in a consistent way.
Because I think we have to leave. But I'm very curious about, so you talk about internal merge versus external merge, but sometimes you have two competing items for internal merge.
Mm-hmm.
And is this, does this algebra describe the fact that if the two, and this is strictly depending on the category, so if they have the same category, the same label, you always pick the closest to the root. So that's the closest, what minimal search used to be. That you get the closest to you, subject over object, for instance.
Yeah, so minimal search, I think in this formulation would also work in the sense that here minimal search is essentially optimizing this cost of where you search for the accessible term, and so you have like a cost of extracting, which depends on how far it is from the root, and the cost of canceling the corresponding copy, which also is so
in a sense, yeah, you want this cost to be balanced. And so again, in those situations, there would be like one choice that balances the cost and one that doesn't. And so, yeah, that would allow you to distinguish the two possibilities. I think that should be compatible with. Yeah.
Sorry, I think we need to leave. Wow, yeah, at least we have the room until 1:45. We can also stay here and talk for a long time, but I think we can thank Matilde and Minka. Thank you very much. If you have any questions, you can ask tomorrow. I will say another time when she's over. So she's not here tomorrow, so now. Okay, so I don't know what plan we have for now. We were asking for lunch, so some of us can stay for lunch, some need to leave because we will have. I don't know who I emailed for your. I don't know. If you're not, I guess maybe you understand what we're doing.
This is a strange situation. Well, we go for lunch because you need lunch. But, did anyone arrange for lunch?
No, I don't know what the plan is. I mean, I suppose that was going to be like.
Or the mathematicians. But I don't know any mathematicians. So
Yeah, no, so the mathematician, I think, no, so Gunther has to go because they have an exam at the department, so he will not come to lunch. So I think, yeah, we can just decide whatever we want. I don't know if Roberta has arranged anything. Or
no, I can do that. We go to the faculty lounge, for instance. Yeah, okay then. Is that safe? Your secrets? I don't know.
Yes.
Thank you so much.
Okay, so really, what
I had a question about the weighting of the deletion and the searching down, because you said that to solve the question of how to look at another tree. And in that case, I saw because that tree was smaller, so the cost of deletion would have.
Yeah, so the thing, like, in an example like that one, why the searching this, looking this compared to this same tree would be less costly than the other one, because, okay, the other one is closer to the root, but
A greater proportion would be
the
deleted.
cost of deletion. And so, yeah, that's.
What if you had two comparably complex trees with a similar size?
Yeah, because there could be like some boundary, like some kind of boundary cases where you put that by coincidence. So we would like this. So it's